26 Chemistry. Organic chemistry, some basic principles and techniques. After studying this unit, you will be able to understand reasons for tetravalence of carbon and shapes of organic molecules, write structures of organic molecules in various ways, classify the organic compounds, name the compounds according to Upac system of nomenclature, and also derive their structures from the given names, understand the concept of organic reaction mechanism, explain the influence of electronic displacements on structure and reactivity of organic compounds, recognize the types of organic reactions, learn the techniques of purification of organic compounds, write the chemical reactions involved in the qualitative analysis of organic compounds, understand the principles involved in quantitative analysis of organic compounds. In the previous unit you have learnt that the element carbon has the unique property called catenation, due to which it forms covalent bonds with other carbon atoms. It also forms covalent bonds with atoms of other elements like hydrogen, oxygen, nitrogen, sulfur, phosphorus, and halogens. The resulting compounds are studied under a separate branch of chemistry called organic chemistry. This unit incorporates some basic principles and techniques of analysis required for understanding the formation and properties of organic compounds. 12.1 General Introduction. Organic compounds are vital for sustaining life on Earth and include complex molecules like genetic information bearing deoxyribonucleic acid, DNA, and proteins that constitute essential compounds of our blood, muscles, and skin. Organic chemicals appear in materials like clothing, fuels, polymers, dyes, and medicines. These are some of the important areas of application of these compounds. Science of organic chemistry is about 200 years old. Around the year 1780, chemists began to distinguish between organic compounds obtained from plants and animals and inorganic compounds prepared from mineral sources. Berzelius, a Swedish chemist, proposed that a vital force was responsible for the formation of organic compounds. However, this notion was rejected in 1828 when F. Wohler synthesized an organic compound, urea, from an inorganic compound, ammonium cyanate. 422 heat NHCNO NH ammonium cyanate urea. The pioneering synthesis of acetic acid by Kolbe, 1845, and that of methane by Berthelot, 1856, showed conclusively that organic compounds could be synthesized from inorganic sources in a laboratory. Unit 12. Organic Chemistry, Some Basic Principles and Techniques. 327. The development of electronic theory of covalent bonding ushered organic chemistry into its modern shape. 12.2 Tetravalence of carbon, shapes of organic compounds. 12th February 2001. The shapes of carbon compounds. The knowledge of fundamental concepts of molecular structure helps in understanding and predicting the properties of organic compounds. You have already learnt theories of valency and molecular structure in Unit 4. Also, you already know that tetravalence of carbon and the formation of covalent bonds by it are explained in terms of its electronic configuration and the hybridization of s and p orbitals. It may be recalled that formation and the shapes of molecules like methane, CH4, ethene, C2H4, ethine, C2H2, are explained in terms of the use of sp3, sp2 and sp hybrid orbitals by carbon atoms in the respective molecules. Hybridization influences the bond length and bond enthalpy, strength, in organic compounds. The sp hybrid orbital contains more s character, and hence it is closer to its nucleus and forms shorter and stronger bonds than the sp3 hybrid orbital. The sp2 hybrid orbital is intermediate in s character between sp and sp3 and, hence, the length and enthalpy of the bonds it forms are also intermediate between them. The change in hybridization affects the electronegativity of carbon. The greater the s character of the hybrid orbitals, the greater is the electronegativity. Thus, a carbon atom having an sp hybrid orbital with 50% s character is more electronegative than that possessing sp2 or sp3 hybridized orbitals. This relative electronegativity is reflected in several physical and chemical properties of the molecules concerned, about which you will learn in later units. 12th February 2002. Some characteristic features of pi bonds. In a pi bond formation, parallel orientation of the two p orbitals on adjacent atoms is necessary for a proper sideways overlap. Thus, in H to C is equal to CH2 molecule, all the atoms must be in the same plane. The p orbitals are mutually parallel and both the p orbitals are perpendicular to the plane of the molecule. Rotation of one CH2 fragment with respect to other interferes with maximum overlap of p orbitals and, therefore, such rotation about carbon-carbon double bond, C is equal to C, is restricted. The electron charge cloud of the pi bond is located above and below the plane of bonding atoms. This results in the electrons being easily available to the attacking regions. In general, pi bonds provide the most reactive centers in the molecules containing multiple bonds. Problem 12.1. How many sigma and pi bonds are present in each of the following molecules? A. HCCCH is equal to CHCH3. B. CH2 is equal to C is equal to CHCH3. Solution. A. Sigma C. C4. Sigma C. H6. Pi C is equal to C1. Pi CC2. B. Sigma C. C3. Sigma C. H6. Pi C is equal to C2. Problem 12.2. What is the type of hybridization of each carbon in the following compounds? A. CH3Cl. B. CH3 to CO. C. CH3CN. D. HCONH2. E. CH3CH is equal to CHCN. Solution. A. sp3. B. sp3. sp2C. sp3. sp.D. sp2E. sp3. sp2. sp2. sp. Problem 12.3. Write the state of hybridization of carbon in the following compounds and shapes of each of the molecules. A. H to C is equal to O. B. CH3F. C. HCN. Solution. A. sp2 hybridized carbon, trigonal planar. B. sp3 hybridized carbon, tetrahedral. C. sp hybridized carbon, linear. 328 Chemistry. 12.3 Structural representations of organic compounds. 12.3.1 Complete, condensed, and bondline structural formulas. Structures of organic compounds are represented in several ways. The Lewis structure or dot structure, dash structure, condensed structure, and bond-line structural formulas are some of the specific types. The Lewis structures, however, can be simplified by representing the two-electron covalent bond by a dash. Such a structural formula focuses on the electrons involved in bond formation. A single dash represents a single bond, double dash is used for double bond, and a triple dash represents triple bond. Lone pairs of electrons on heteroatoms, example, oxygen, nitrogen, sulfur, halogens, etc., may or may not be shown. Thus, ethane, C2H6, ethene, C2H4, ethine, C2H2, and methanol, CH3O, can be represented by the following structural formulas. Such structural representations are called complete structural formulas. Similarly, CH3CH2CH2CH2CH2CH2CH2CH3 can be further condensed to CH3, CH2, 6CH3. For further simplification, organic chemists use another way of representing the structures in which only lines are used. In this bond line structural representation of organic compounds, carbon and hydrogen atoms are not shown and the lines representing carbon-carbon bonds are drawn in a zigzag fashion. The only atoms specifically written are oxygen, chlorine, nitrogen, etc. The terminals denote methyl, CH3, groups unless indicated otherwise by a functional group, while the line junctions denote carbon atoms bonded to appropriate number of hydrogens required to satisfy the valency of the carbon atoms. Some of the examples are represented as follows. 3-methyloctane can be represented in various forms as A. CH3CH2CH2CH2CH2CH2CH3 vertical bar CH3. These structural formulas can be further abbreviated by omitting some or all of the dashes representing covalent bonds and by indicating the number of identical groups attached to an atom by a subscript. The resulting expression of the compound is called a condensed structural formula. Thus, ethane, ethene, ethine and methanol can be written as CH3CH3H2C is equal to CH2HCCH CH3O. Ethane, ethene, ethine, methanol. Ethane, ethene. Ethyne, methanol. 2. Various ways of representing to bromobutane are A. CH3CHBrCH to CH3B. C. B. C. Organic chemistry. Some basic principles and techniques 329 in cyclic compounds. The bond line formulas may be given as follows. Cyclopropane. Cyclopentane. Chlorocyclohexane. Problem 12.4. Expand each of the following condensed formulas into their complete structural formulas. A. CH3CH to COH to CH3, B. CH3CH is equal to CH, CH2, 3CH3 solution. B. Solution condensed formula A. Who, CH2, 3CH, CH3, CH, CH3, 2, B. Hoch, CN, to bondline formula. A. B. Problem 12.5. For each of the following compounds, write a condensed formula and also their bondline formula. A. Hoch to CH to CH to CH, CH3, CH, CH3, CH3. B. A. Problem 12.6. Expand each of the following bondline formulas to show all the atoms including carbon and hydrogen. A. B. C. D. Solution. 330 Chemistry. Framework model ball and stick model. Space filling model. Fig. 12.2. 12th March 2002 three-dimensional representation of organic molecules. The three-dimensional 3-D structure of organic molecules can be represented on paper by using certain conventions. For example, by using solid and dashed wedge formula, the 3-D image of a molecule from a two-dimensional picture can be perceived. In these formulas, the solid ridge is used to indicate a bond projecting out of the plane of paper towards the observer. The dash ridge is used to depict the bond projecting out of the plane of the paper and away from the observer. Wedges are shown in such a way that the broad end of the wedge is towards the observer. The bonds lying in plane of the paper are depicted by using a normal line. 3-D representation of methane molecule on paper has been shown in Fig. 12.1. Fig. 12.1 Wedge representation of CH4. Molecular models. Molecular models are physical devices that are used for a better visualization and perception of three-dimensional shapes of organic molecules. These are made of wood, plastic or metal, and are commercially available. Commonly, three types of molecular models are used: 1. Framework model, 2. Ball and stick model, and 3. Space-filling model. In the framework model, only the bonds connecting the atoms of a molecule, and not the atoms themselves, are shown. This model emphasizes the pattern of bonds of a molecule while ignoring the size of atoms. In the ball and stick model, both the atoms and the bonds are shown. Balls represent atoms, and the stick denotes a bond. Compounds containing C is equal to C, example, ethene, can best be represented by using springs in place of sticks. These models are referred to as ball and spring model. The space-filling model emphasizes the relative size of each atom based on its van der Waals radius. Bonds are not shown in this model. It conveys the volume occupied by each atom in the molecule. In addition to these models, computer graphics can also be used for molecular modeling. Organic chemistry, some basic principles and techniques. 331. 12.4 Classification of organic compounds. The existing large number of organic compounds and their ever-increasing numbers has made it necessary to classify them on the basis of their structures. Organic compounds are broadly classified as follows. I. Acyclic or open-chain compounds. These compounds are also called as aliphatic compounds and consist of straight or branched chain compounds, for example. Homocyclic. Sometimes atoms other than carbon are also present in the ring. Heterocyclic. Some examples of this type of compounds are cyclopropane cyclohexane, cyclohexene tetrahydrofuran. These exhibit some of the properties similar to those of aliphatic compounds. Aromatic compounds. Aromatic compounds are special types of compounds. You will learn about these compounds in detail in Unit 13. These include benzene and other related ring compounds, benzenoid. Like alicyclic compounds, aromatic compounds may also have heteroatom in the ring. Such compounds are called heterocyclic aromatic compounds. Some of the examples of various types of aromatic compounds are benzenoid aromatic compounds, benzene aniline naphthalene, non-benzenoid compound, tropolone, isobutane, acetaldehyde acetic acid, CH3CH3, ethane. Two alicyclic or closed chain or ring compounds. Alicyclic, aliphatic cyclic compounds contain carbon atoms joined in the form of a ring. 332 Chemistry. Heterocyclic aromatic compounds. Furan thiophene pyridine. Organic compounds can also be classified on the basis of functional groups into families or homologous series. Functional group. The functional group may be defined as an atom or group of atoms joined in a specific manner, which is responsible for the characteristic chemical properties of the organic compounds. The examples are hydroxyl group, O, aldehyde group, CHO, and carboxylic acid group, CU, etc. Homologous series. A group or a series of organic compounds, each containing a characteristic functional group, forms a homologous series, and the members of the series are called homologues. The members of a homologous series can be represented by general molecular formula, and the successive members differ from each other in molecular formula by a CH2 unit. There are a number of homologous series of organic compounds. Some of these are alkanes, alkenes, alkynes, halolcanes, alkanols, alkanils, alkanones, alkanoic acids, amines, etc. 12.5 Nomenclature of organic compounds. Organic chemistry deals with millions of compounds. In order to clearly identify them, a systematic method of naming has been developed and is known as the Upac, International Union of Pure and Applied Chemistry, System of Nomenclature. In this systematic nomenclature, the names are correlated with the structure such that the reader or listener can deduce the structure from the name. Before the Upac system of nomenclature, however, organic compounds were assigned names based on their origin or certain properties. For instance, citric acid is named so because it is found in citrus fruits, and the acid found in red and is named formic acid since the Latin word for and is formica. These names are traditional and are considered as trivial or common names. Some common names are followed even today. For example, Buckminster fullerene is a common name given to the newly discovered C60 cluster, a form of carbon, noting its structural similarity to the geodesic domes popularized by the famous architect R. Buckminster Fuller. Common names are useful and in many cases indispensable, particularly when the alternative systematic names are lengthy and complicated. Common names of some organic compounds are given in Table 12.1. Table 12.1 Common or trivial names of some organic compounds. 12th May 2001 The Upac system of nomenclature. A systematic name of an organic compound is generally derived by identifying the parent hydrocarbon and the functional groups attached to it. See the example given below. Organic chemistry, some basic principles and techniques 333. By further using prefixes and suffixes, the parent name can be modified to obtain the actual name. Compounds containing carbon and hydrogen only are called hydrocarbons. A hydrocarbon is termed saturated if it contains only carbon-carbon single bonds. The Upac name for a homologous series of such compounds is alkane. Paraffin, Latin, little affinity, was the earlier name given to these compounds. Unsaturated hydrocarbons are those which contain at least one carbon-carbon double or triple bond. 12th May 2002 Upac nomenclature of alkanes. Straight-chain hydrocarbons. The names of such compounds are based on their chain structure and end with suffix ane and carry a prefix indicating the number of carbon atoms present in the chain, except from CH4 to C4H10, where the prefixes are derived from trivial names. The Upac names of some straight-chain saturated hydrocarbons are given in Table 12.2. The alkanes in Table 12.2 differ from each other by merely the number of CH2 groups in the chain. They are homologues of alkane series. In order to name such compounds, the names of alkyl groups are prefixed to the name of parent alkane. An alkyl group is derived from a saturated hydrocarbon by removing a hydrogen atom from carbon. Thus, CH4 becomes CH3 and is called methyl group. An alkyl group is named by substituting vial for ane in the corresponding alkane. Some alkyl groups are listed in Table 12.3. Table 12.3 Some alkyl groups. Table 12.2 Upac names of some unbranched saturated hydrocarbons. Branched chain hydrocarbons. In a branched chain compound, small chains of carbon atoms are attached at one or more carbon atoms of the parent chain. The small carbon chains, branches, are called alkyl groups. For example, CH3, CH, CH2, CH3, CH3, CH, CH2, CH, CH3, CH3, CH2, CH3, CH3. A, B. Abbreviations are used for some alkyl groups. For example, methyl is abbreviated as Me, ethyl as Et, propyl as PR, and butyl as Bu. The alkyl groups can be branched also. Thus, propyl and butyl groups can have branched structures as shown below. CH3CH3CH to CH3CH2. CH3CH3CH3. Isopropyl sec-butyl isobutyl CH3CH3. CH3CCH3CCH2. CH3CH3 terbutyl neopentyl. Common branched groups have specific trivial names. For example, the propyl groups can either be N-propyl group or isopropyl group. The branched butyl groups are called sec-butyl, isobutyl, and terbutyl group. We also encounter the structural unit CH to C, CH3, 3, which is called neopentyl group. Nomenclature of branched chain alkanes. We encounter a number of branched chain alkanes. The rules for naming them are given below. 334 Chemistry. Separated from the groups by hyphens, and there is no break between methyl and nonane dot. 4. If two or more identical substituent groups are present, then the numbers are separated by commas. The names of identical substituents are not repeated. Instead, prefixes such as D for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, etc. are used. While writing the name of the substituents in alphabetical order, these prefixes, however, are not considered. Thus, the following compounds are named as CH3CH3CH3CH3, CH3CHCH to CHCH3CH3CCH to CHCH3, CH3, 2,4-dimethylpentane 2,4-trimethylpentane, H3CH to CCH3, CH3CH to CHCCH to CH to CH3, CH3, 3-ethyl 4,4-dimethylheptane. 5. If the two substituents are found in equivalent positions, the lower number is given to the one coming first in the alphabetical listing. Thus, the following compound is 3-ethyl 6-methyloctane and not 6-ethyl 3-methyloctane. 1, 2, 3, 4, 5, 6, 7, 8 CH3, CH2, CH, CH2, CH2, CH, CH2, CH3, CH2, CH3, CH3. 6. The branched alkyl groups can be named by following the above-mentioned procedures. However, the carbon atom of the branch that attaches to the root alkane is numbered 1 as exemplified below. 4, 3 to 1 CH3, CH, CH2, CH. CH3, CH3, 1, 3-dimethylbutyl. 1. First of all, the longest carbon chain in the molecule is identified. In the example I, given below, the longest chain has 9 carbons and it is considered as the parent or root chain. Selection of parent chain as shown in 2 is not correct because it has only 8 carbons. 1 to 3 4 5 1 to 3 4 5 1 to 3 4 5 6 7 2. The carbon atoms of the parent chain are numbered to identify the parent alkane and to locate the positions of the carbon atoms at which branching takes place due to the substitution of alkyl group in place of hydrogen atoms. The numbering is done in such a way that the branched carbon atoms get the lowest possible numbers. Thus, the numbering in the above example should be from left to right, branching at carbon atoms 2 and 6, and not from right to left, giving numbers 4 and 8 to the carbon atoms at which branches are attached. 1 to 3 4 5 6 7 8 9 C C C C C C C C C C C C 9 8 7 6 5 4 3 2 1 C C C C C C C C C C C C 3. The names of alkyl groups attached as a branch are then prefixed to the name of the parent alkane and position of the substituents is indicated by the appropriate numbers. If different alkyl groups are present, they are listed in alphabetical order. Thus, name for the compound shown above is 6-ethyl-2-methylonane. Note, the numbers are Organic Chemistry, Some Basic Principles and Techniques 335. The name of such branched chain, alkyl group, is placed in parentheses while naming the compound. While writing the trivial names of substituents in alphabetical order, the prefixes ISO and NEO are considered to be the part of the fundamental name of alkyl group. The prefixes SEC and TERT are not considered to be the part of the fundamental name. The use of ISO and related common prefixes for naming alkyl groups is also allowed by the Upac nomenclature as long as these are not further substituted. In multi-substituted compounds, the following rules may also be remembered. Times if there happens to be two chains of equal size, then that chain is to be selected which contains more number of side chains. Times after selection of the chain, numbering is to be done from the end closer to the substituent. 5. 2-ethylbutyl, 3, 3-dimethyldecaene, and not 5, 2, 2-dimethylbutyl, 3-ethyldecaene. 5-sec-butyl 4-isopropyldecane. 5, 2, 2-dimethylpropyl, nonane. Problem 12.7 Structures and Upac names of some hydrocarbons are given below. Explain why the names given in the parentheses are incorrect. 3-ethyl 1,1-dimethylcyclohexane, not 1-ethyl 3,3-dimethylcyclohexane. 2, 5, 6-trimethyl-octane, and not 3, 4, 7-trimethyl-octane. 3-ethyl 5-methylheptane, and not 5-ethyl 3-methylheptane. Cyclic compounds, a saturated monocyclic compound, is named by prefixing cyclo to the corresponding straight chain alkane. If side chains are present, then the rules given above are applied. Names of some cyclic compounds are given below. Solution. A. Lowest locant number, 2, 5, 6 is lower than 3, 5, 7. B. Substituents are in equivalent position. Lower number is given to the one that comes first in the name according to alphabetical order. 12th May 2003 Nomenclature of organic compounds having functional groups. A functional group, as defined earlier, is an atom or a group of atoms bonded together in a unique manner, which is usually the site of 336 Chemistry. Chemical reactivity in an organic molecule. Compounds having the same functional group undergo similar reactions. For example, CH3O, CH3CH2O, and CH3, all having O functional group liberate hydrogen on reaction with sodium metal. The presence of functional groups enables systematization of organic compounds into different classes. Examples of some functional groups with their prefixes and suffixes, along with some examples of organic compounds possessing these, are given in Table 12.4. First of all, the functional group present in the molecule is identified, which determines the choice of appropriate suffix. The longest chain of carbon atoms containing the functional group is numbered in such a way that the functional group is attached at the carbon atom possessing lowest possible number in the chain. By using the suffix as given in Table 12.4, the name of the compound is arrived at. In the case of polyfunctional compounds, one of the functional groups is chosen as the principal functional group, and the compound is then named on that basis. The remaining functional groups, which are subordinate functional groups, are named as substituents using the appropriate prefixes. The choice of principal functional group is made on the basis of order of preference. The order of decreasing priority for some functional groups is Q. So 3H, Cur, R is equal to alkyl group, COCl, COM2, CN, dash HC is equal to O, C is equal to O, O, NH2, C is equal to C, CC. The R, C6H5, halogens, F, Cl, Br, I, NO2, alkoxy, or etc. are always prefix substituents. Thus, a compound containing both an alcohol and a keto group is named as hydroxylcanone, since the keto group is preferred to the hydroxyl group. For example, HOCH2, CH2, 3CH2 COCH3 will be named as 7-hydroxyheptane to 1 and not as 2-oxyheptane 7-ol. Similarly, BrCH to CH is equal to CH2 is named as 3-bromoprop-1 Na and not 1-bromoprop-2 Na. If more than one functional group of the same type are present, their number is indicated by adding D, tri, etc. before the class suffix. In such cases, the full name of the parent, alkane, is written before the class suffix. For example, CH2O, CH2O is named as ethane, 1,2-diol. However, the ending, ne of the parent alkane is dropped in the case of compounds having more than one double or triple bond. For example, CH2 is equal to CH is equal to CH2 is named as buta, 1,3-diene. Problem 12.8. Write the Upac names of the compounds I4 from their given structures. Solution. Times the functional group present is an alcohol, O. Hence the suffix is ol. Times the longest chain containing O has 8 carbon atoms. Hence the corresponding saturated hydrocarbon is octane. Times the O is on carbon atom 3. In addition, a methyl group is attached at 6th carbon. Hence, the systematic name of this compound is 6-methyloctane 3-ol. Solution. The functional group present is ketone, C is equal to O, hence suffix 1. Presence of two keto groups is indicated by D, hence suffix becomes dione. The two keto groups are at carbons 2 and 4. The longest chain contains 6 carbon atoms, hence, parent hydrocarbon is hexane. Thus, the systematic name is hexane 2,4-dione. Organic chemistry, some basic principles and techniques 337. Table 12.4 Some functional groups and classes of organic compounds. 338 Chemistry. Solution. Here, two functional groups, namely ketone and carboxylic acid, are present. The principal functional group is the carboxylic acid group, hence the parent chain will be suffixed with OIC acid. Numbering of the chain starts from carbon of two functional group. The keto group in the chain at carbon 5 is indicated by OXO. The longest chain, including the principal functional group, has 6 carbon atoms, hence the parent hydrocarbon is hexane. The compound is, therefore, named as 5-oxohexanonic acid. Solution. The 2C is equal to C functional groups are present at carbon atoms 1 and 3, while the CC functional group is present at carbon 5. These groups are indicated by suffixes diene and yene respectively. The longest chain containing the functional groups has 6 carbon atoms, hence the parent hydrocarbon is hexane. The name of compound, therefore, is hexa 1,3-diene-5-yene. Problem 12.9. Derive the structure of I2-chlorohexane, 2-pent-4-N2-ol, 3-nitrocyclohexane, 4-cyclohex-2-N1-ol, V6-hydroxyheptanyl. Solution. Hexane indicates the presence of 6 carbon atoms in the chain. The functional group chloro is present at carbon 2. Hence, the structure of the compound is CH3CH2CH2CH2CH, Cl, CH3. 2. Pent indicates that parent hydrocarbon contains 5 carbon atoms in the chain. N and ol correspond to the functional groups C is equal to C and O at carbon atoms 4 and 2 respectively. Thus, the structure is CH2 is equal to CHCH to CH, O, CH3. 3. 6-membered ring containing a carbon-carbon double bond is implied by cyclohexene, which is numbered as shown in I. The prefix 3-nitro means that a nitro group is present on C3. Thus, complete structural formula of the compound is 2. Double bond is suffixed functional group whereas number 2 is prefixed functional group, therefore double bond gets preference over no 2 group. 4. 1-ol means that AO group is present at C1. O is suffixed functional group and gets preference over C is equal to C bond. Thus the structure is as shown in 2. Heptanyl indicates the compound to be an aldehyde containing 7 carbon atoms in the parent chain. The 6-hydroxy indicates that O group is present at carbon 6. Thus, the structural formula of the compound is a CH3CH, O, CH2CH2CH2CH2 CH2. Carbon atom of CHO group is included while numbering the carbon chain. 12th May 2004 Nomenclature of substituted benzene compounds. For Upac nomenclature of substituted benzene compounds, the substituent is placed as prefix to the word benzene as shown in the following examples. However, common names, written in bracket below, of many substituted benzene compounds are also universally used. Organic chemistry. Some basic principles and techniques 339. 2-chloro-4-methylenizole 4-ethyl-2-methylaniline. 1-chloro-2,4-dinitrobenzene, not 4-chloro, 1,3-dinitrobenzene. If benzene ring is disubstituted, the position of substituents is defined by numbering the carbon atoms of the ring such that the substituents are located at the lowest numbers possible. For example, the compound B is named as 1,3-dibromobenzene and not as 1,5-dibromobenzene. Substituent of the base compound is assigned number 1, and then the direction of numbering is chosen such that the next substituent gets the lowest number. The substituents appear in the name in alphabetical order. Some examples are given below. 2-chloro-1-methyl-4-nitrobenzene, not 4-methyl-5-chloro-nitrobenzene. 3,4-dimethylphenyl. Methylbenzene, methoxybenzene, aminobenzene, toluene, anisole, aniline. Nitrobenzene, bromobenzene. 1,2-dibromobenzene 1,3-dibromobenzene 1,4-dibromobenzene. A, B, C. In the trivial system of nomenclature, the terms ortho, O, meta, M, and para, P, are used as prefixes to indicate the relative positions 1, 2, 1, 3, and 1, 4 respectively. Thus, 1, 3-dibromobenzene, B, is named as M-dibromobenzene, meta is abbreviated as M, and the other isomers of dibromobenzene 1, 2, A, and 1, 4, C, are named as ortho, or just O, and para, or just P, dibromobenzene, respectively. For tri or higher substituted benzene derivatives, these prefixes cannot be used and the compounds are named by identifying substituent positions on the ring by following the lowest locant rule. In some cases, common name of benzene derivatives is taken as the base compound. When a benzene ring is attached to an alkane with a functional group, it is considered as substituent instead of a parent. The name for benzene as substituent is phenyl, C6H5, also abbreviated as PH. 340 Chemistry. Different carbon skeletons, these are referred to as chain isomers, and the phenomenon is termed as chain isomerism. For example, C5H12 represents 3 compounds. Isomerism. Structural isomerism, stereoisomerism. Chain isomerism, position isomerism, functional group isomerism. Metamerism, geometrical isomerism, optical isomerism. 12.6 Isomerism. The phenomenon of existence of 2 or more compounds possessing the same molecular formula but different properties is known as isomerism. Such compounds are called as isomers. The following flow chart shows different types of isomerism. 12th June 2001 Structural isomerism. Compounds having the same molecular formula but different structures, manners in which atoms are linked, are classified as structural isomers. Some typical examples of different types of structural isomerism are given below. I. Chain isomerism, when 2 or more compounds have similar molecular formula but A, B, C, D. Problem 12.10. Write the structural formula of A. O-ethylenisole, B. P-nitroaniline, C. 2,3-dibromo-1 phenylpentane, D. 4-ethyl-1-fluoro-2-nitrobenzene. Solution. CH3. CH3 CH2 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 CH3 CH3 CHCH to CH3 pentane isopentane to methylbutane. CH3 CH3C CH3 CH3 neopentane 2 to dimethylpropane. 2. Position isomerism, when 2 or more compounds differ in the position of substituent atom or functional group on the carbon skeleton, they are called position isomers, and this phenomenon is termed as position isomerism. For example, the molecular formula C3H8O represents 2 alcohols. O. CH3CH2CH2O CH3CH CH3 propan 1 ol propan 2 ol. 3. Functional group isomerism, 2 or more compounds having the same molecular formula but different functional groups are called functional isomers, and this phenomenon is termed as functional group isomerism. For example, the molecular formula C3H6O represents an aldehyde and a ketone. Organic chemistry, some basic principles and techniques 341. OHCH3CCH3CH3CH2, C is equal to O. Propanone propanol. 4. Metamerism, it arises due to different alkyl chains on either side of the functional group in the molecule. For example, C4H10O represents methoxypropane, CH3OC3H7, and ethoxythane, C2H5OC2H5. 12th June 2002 Stereoisomerism. The compounds that have the same constitution and sequence of covalent bonds but differ in relative positions of their atoms or groups in space are called stereoisomers. This special type of isomerism is called as stereoisomerism and can be classified as geometrical and optical isomerism. 12.7 Fundamental concepts in organic reaction mechanism. In an organic reaction, the organic molecule, also referred as a substrate, reacts with an appropriate attacking reagent and leads to the formation of one or more intermediates and finally products. The general reaction is depicted as follows. Understanding the reactivity of organic compounds and in planning strategy for their synthesis. In the following sections, we shall learn some of the principles that explain how these reactions take place. 12th July 2001 Fission of a covalent bond. A covalent bond can get cleaved either by I. Heterolytic cleavage or by 2. Homolytic cleavage. In heterolytic cleavage, the bond breaks in such a fashion that the shared pair of electrons remains with one of the fragments. After heterolysis, one atom has a sextet electronic structure and a positive charge and the other, a valence octet with at least one lone pair and a negative charge. Thus, heterolytic cleavage of bromomethane will give CH3 and Br, as shown below. A species having a carbon atom possessing sextet of electrons and a positive charge is called a carbocation, earlier called carbonium ion. The CH3 ion is known as a methyl cation or methyl carbonium ion. Carbocations are classified as primary, secondary or tertiary depending on whether 1, 2 or 3 carbons are directly attached to the positively charged carbon. Some other examples of carbocations are CH3C plus H2, ethyl cation, a primary carbocation, CH3 to C plus H, isopropyl cation, a secondary carbocation, and CH3, 3C plus, tert-butyl cation, a tertiary carbocation. Carbocations are highly unstable and reactive species. Alkyl groups directly attached to the positively charged carbon stabilize the carbocations due to inductive and hyperconjugation effects, which you will be studying in the sections 12th July 2005 and 12th July 2009. The observed order of carbocation stability is C plus H3CH3 C plus H2, CH3 to C plus H, CH3, 3C plus. These carbocations have trigonal planar shape with positively charged carbon being sp2 hybridized. Thus, the shape of C plus H3 may be considered as being derived from the overlap of 3 equivalent C, sp2, hybridized orbitals. Organic molecule, substrate. Intermediate, products attacking reagent. Byproducts. Substrate is that reactant which supplies carbon to the new bond and the other reactant is called reagent. If both the reactants supply carbon to the new bond, then choice is arbitrary, and in that case the molecule on which attention is focused is called substrate. In such a reaction, a covalent bond between 2 carbon atoms or a carbon and some other atom is broken and a new bond is formed. A sequential account of each step, describing details of electron movement, energetics during bond cleavage and bond formation, and the rates of transformation of reactants into products, kinetics, is referred to as reaction mechanism. The knowledge of reaction mechanism helps in 342 chemistry. With 1s orbital of each of the 3 hydrogen atoms. Each bond may be represented as C, sp2, H1s, sigma bond. The remaining carbon orbital is perpendicular to the molecular plane and contains no electrons. Fig. 12.3. Fig. 12.3 Shape of methyl cation. The heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons. For example, when group Z attached to the carbon leaves without electron pair, the methyl anion is formed. Such a carbon species carrying a negative charge on carbon atom is called carbanion. Carbanions are also unstable and reactive species. The organic reactions which proceed through heterolytic bond cleavage are called ionic or heteropolar or just polar reactions. In homolytic cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atoms. Thus, in homolytic cleavage, the movement of a single electron takes place instead of an electron pair. The single electron movement is shown by half-headed, fishhook, curved arrow. Such cleavage results in the formation of neutral species, atom or group, which contains an unpaired electron. These species are called free radicals. Like carbocations and carbanions, free radicals are also very reactive. A homolytic cleavage can be shown as alkyl free radical. Alkyl radicals are classified as primary, secondary, or tertiary. Alkyl radical stability increases as we proceed from primary to tertiary. Methyl ethyl isopropyl tert-butyl free radical organic reactions, which proceed by homolytic fission, are called free radical or homopolar or nonpolar reactions. 12th July 2002 Nucleophiles and Electrophiles. A reagent that brings an electron pair is called nucleophile, NuI, nucleus seeking, and the reaction is then called nucleophilic. A reagent that takes away an electron pair is called electrophile, E+, I, electron seeking, and the reaction is called electrophilic. During a polar organic reaction, a nucleophile attacks an electrophilic center of the substrate, which is that specific atom or part of the electrophile that is electron deficient. Similarly, the electrophiles attack at nucleophilic center, which is the electron-rich center of the substrate. Thus, the electrophiles receive electron pair from nucleophile when the two undergo bonding interaction. A curved arrow notation is used to show the movement of an electron pair from the nucleophile to the electrophile. Some examples of nucleophiles are the negatively charged ions with lone pair of electrons such as hydroxide, O, cyanide, NC, ions and carbanions, R3C. Neutral molecules such as etc. can also act as nucleophiles due to the presence of lone pair of electrons. Examples of electrophiles include carbocations, CH3, and neutral molecules having functional groups like carbonyl group, C is equal to O, or alkyl halides, R3CX, where X is a halogen atom. The carbon atom in carbocations has sextet configuration, hence, it is electron deficient and can receive a pair of electrons from the nucleophiles. In neutral molecules, such as alkyl halides, due to the polarity of the CX bond, a partial positive charge is generated. Organic chemistry, some basic principles and techniques 343. On the carbon atom, and hence the carbon atom becomes an electrophilic center, at which a nucleophile can attack. Problem 12.11. Using curved arrow notation, show the formation of reactive intermediates when the following covalent bonds undergo heterolytic cleavage. A. CH3, SCH3, B. CH3, CN, C. CH3, Cu. Solution. Problem 12.12. Giving justification, categorize the following molecules ions as nucleophile or electrophile. Solution. Nucleophiles, 25 3 to 3 Hs, CHO, CHN, HN. These species have unshared pair of electrons, which can be donated and shared with an electrophile. Electrophiles, BF, Cl, CHCO, no 33-2. Reactive sites have only 6 valence electrons, can accept electron pair from a nucleophile. Problem 12.13 Identify electrophilic center in the following. CH3CH is equal to O, CH3CN, CH3I. Solution among CH3HC asterisk is equal to O, H3CC asterisk N, and H3C asterisk I. The star carbon atoms are electrophilic centers, as they will have partial positive charge due to polarity of the bond. 12th July 2003 Electron movement in organic reactions. The movement of electrons in organic reactions can be shown by curved arrow notation. It shows how changes in bonding occur due to electronic redistribution during the reaction. To show the change in position of a pair of electrons, curved arrow starts from the point from where an electron pair is shifted and it ends at a location to which the pair of electron may move. Presentation of shifting of electron pair is given below. I. From pi bond to adjacent bond position. 2. From pi bond to adjacent atom. 3. From atom to adjacent bond position movement of single electron is indicated by a single barbed fish hooks, i.e. half-headed curved arrow. For example, in transfer of hydroxide ion giving ethanol, and in the dissociation of chloromethane, the movement of electron using curved arrows can be depicted as follows. 12th July 2004 Electron displacement effects in covalent bonds. The electron displacement in an organic molecule may take place either in the ground state under the influence of an atom or a substituent group or in the presence of an appropriate attacking reagent. The electron displacements due to the influence of an atom or a substituent group present in the molecule cause permanent polarization of the bond. Inductive effect and resonance effects are examples of this type of electron displacements. Temporary electron displacement effects are seen in a molecule. 344 Chemistry. When a reagent approaches to attack it, this type of electron displacement is called electromeric effect or polarizability effect. In the following sections, we will learn about these types of electronic displacements. 12th July 2005 Inductive effect. When a covalent bond is formed between atoms of different electronegativity, the electron density is more towards the more electronegative atom of the bond. Such a shift of electron density results in a polar covalent bond. Bond polarity leads to various electronic effects in organic compounds. Let us consider chloroethane, CH3CH2Cl, in which the C-Cl bond is a polar covalent bond. It is polarized in such a way that the carbon 1 gains some positive charge, delta plus, and the chlorine some negative charge, delta. The fractional electronic charges on the two atoms in a polar covalent bond are denoted by symbol delta, delta, and the shift of electron density is shown by an arrow that points from delta plus to delta, end of the polar bond. Delta delta plus delta CH3CH2Cl to 1. In turn carbon 1, which has developed partial positive charge, delta plus, draws some electron density towards it from the adjacent C to C bond. Consequently, some positive charge, delta delta plus, develops on carbon 2 also, where delta delta plus symbolizes relatively smaller positive charge as compared to that on carbon 1. In other words, the polar C-Cl bond induces polarity in the adjacent bonds. Such polarization of sigma bond caused by the polarization of adjacent sigma bond is referred to as the inductive effect. This effect is passed on to the subsequent bonds also, but the effect decreases rapidly as the number of intervening bonds increases and becomes vanishingly small after 3 bonds. The inductive effect is related to the ability of substituents to either withdraw or donate electron density to the attached carbon atom. Based on this ability, the substituents can be classified as electron withdrawing or electron donating groups relative to hydrogen, halogens, and many other groups such as nitro, number 2, cyano, CN, carboxy, Cu, ester, -Cur, aryloxy, or e.g., OC6H5, etc. are electron withdrawing groups. On the other hand, the alkyl groups like methyl, CH3, and ethyl, CH2, CH3, are usually considered as electron donating groups. Problem 12.14. Which bond is more polar in the following pairs of molecules? A. H3CH, H3CBr, B. H3CNH2, H3CO, C. H3CO, H3CH. Solution: A. C. Br. Since Br is more electronegative than H, B, C, O, C, C, O. Problem 12.15. In which C bond of CH3CH to CH to Br, the inductive effect is expected to be the least? Solution: magnitude of inductive effect diminishes as the number of intervening bonds increases. Hence, the effect is least in the bond between carbon 3 and hydrogen. 12th July 2006 Resonance structure. There are many organic molecules whose behavior cannot be explained by a single Lewis structure. An example is that of benzene. Its cyclic structure containing alternating C single, and C is equal to C double bonds shown is inadequate for explaining its characteristic properties. As per the above representation, benzene should exhibit to different bond lengths due to C single, and C is equal to C double bonds. However, as determined experimentally, benzene has a uniform C bond distances of 139 pm, a value intermediate between the C single 154 pm and C is equal to C double 134 pm bonds. Thus, the structure of benzene cannot be represented adequately by the above structure. Further, benzene can be represented equally well by the energetically identical structures I and II. Benzene. Organic chemistry, some basic principles and techniques 345. Therefore, according to the resonance theory, Unit 4, the actual structure of benzene cannot be adequately represented by any of these structures, rather it is a hybrid of the two structures, I and II, called resonance structures. The resonance structures, canonical structures or contributing structures, are hypothetical and individually do not represent any real molecule. They contribute to the actual structure in proportion to their stability. Another example of resonance is provided by nitromethane, CH3NO2, which can be represented by two Lewis structures, I and II. There are two types of NO bonds in these structures. However, it is known that the two N-O bonds of nitromethane are of the same length, intermediate between AN-O single bond and AN is equal to O double bond. The actual structure of nitromethane is therefore a resonance hybrid of the two canonical forms I and II. The energy of actual structure of the molecule, the resonance hybrid, is lower than that of any of the canonical structures. The difference in energy between the actual structure and the lowest energy resonance structure is called the resonance stabilization energy or simply the resonance energy. The more the number of important contributing structures, the more is the resonance energy. Resonance is particularly important when the contributing structures are equivalent in energy. The following rules are applied while writing resonance structures. The resonance structures have I, the same positions of nuclei, and 2, the same number of unpaired electrons. Among the resonance structures, the one which has more number of covalent bonds, all the atoms with octet of electrons, except hydrogen which has a duplet, less separation of opposite charges, a negative charge if any on more electronegative atom, a positive charge if any on more electropositive atom, and more dispersal of charge, is more stable than others. Problem 12.16. Write resonance structures of CH3Co and show the movement of electrons by curved arrows. Solution. First, write the structure and put unshared pairs of valence electrons on appropriate atoms. Then draw the arrows one at a time, moving the electrons to get the other structures. Problem 12.17. Write resonance structures of CH2 is equal to CH2. Indicate relative stability of the contributing structures. Solution. Stability I to 3. I most stable. More number of covalent bonds. Each carbon and oxygen atom has an octet, and no separation of opposite charge. 2. Negative charge on more electronegative atom and positive charge on more electropositive atom. 3. Does not contribute as oxygen has positive charge and carbon has negative charge, hence least stable. 346 Chemistry. Problem 12.18. Explain why the following two structures, I and 2, cannot be the major contributors to the real structure of CH3COOH3. Solution. The two structures are less important contributors as they involve charge separation. Additionally, structure I contains a carbon atom with an incomplete octet. 12th July 2007 Resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of two pi bonds or between a pi bond and lone pair of electrons present on an adjacent atom. The effect is transmitted through the chain. There are two types of resonance or mesomeric effect designated as R or M effect. I, positive resonance effect, plus R effect. In this effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. This electron displacement makes certain positions in the molecule of high electron densities. This effect in aniline is shown as the atoms or substituent groups, which represent plus R or R electron displacement effects, are as follows. Plus R effect, halogen, O or ochre, NH2, NHR, NR2, NH core, R effect, Q, CHO, C is equal to O, Cn, NO2. The presence of alternate single and double bonds in an open chain or cyclic system is termed as a conjugated system. These systems often show abnormal behavior. The examples are 1,3-butadiene, aniline, and nitrobenzene, etc. In such systems, the pi electrons are delocalized and the system develops polarity. 12th July 2008 Electromeric effect, E effect. It is a temporary effect. The organic compounds having a multiple bond, a double or triple bond, show this effect in the presence of an attacking reagent only. It is defined as the complete transfer of a shared pair of pi electrons to one of the atoms joined by a multiple bond on the demand of an attacking reagent. The effect is annulled as soon as the attacking reagent is removed from the domain of the reaction. It is represented by E, and the shifting of the electrons is shown by a curved arrow. There are two distinct types of electromeric effect. I. Positive electromeric effect plus E effect. In this effect, the pi electrons of the multiple bond are transferred to that atom to which the reagent gets attached. For example, 2. Negative resonance effect, R effect. This effect is observed when the transfer of electrons is towards the atom or substituent group attached to the conjugated system. For example, in nitrobenzene, this electron displacement can be depicted as 2. Negative electromeric effect, E effect. In this effect, the pi electrons of the multiple bond are transferred to that atom to which the attacking reagent does not get attached. For example, Organic Chemistry, Some Basic Principles and Techniques 347. When inductive and electromeric effects operate in opposite directions, the electromeric effect predominates. 12th July 2009 Hyperconjugation. Hyperconjugation is a general stabilizing interaction. It involves delocalization of sigma electrons of C, H bond of an alkyl group directly attached to an atom of unsaturated system or to an atom with an unshared p orbital. The sigma electrons of C, H bond of the alkyl group enter into partial conjugation with the attached unsaturated system or with the unshared p orbital. Hyperconjugation is a permanent effect. To understand hyperconjugation effect, let us take an example of CH-CH3-2 ethyl cation, in which the positively charged carbon atom has an empty p orbital. One of the CH bonds of the methyl group can align in the plane of this empty p orbital, and the electrons constituting the CH bond in plane with this p orbital can then be delocalized into the empty p orbital as depicted in Fig. 12.4a. In general, greater the number of alkyl groups attached to a positively charged carbon atom, the greater is the hyperconjugation interaction and stabilization of the cation. Thus, we have the following relative stability of carbocations. Fig. 12.4b. Orbital diagram showing hyperconjugation in propene. Fig. 12.4a. Orbital diagram showing hyperconjugation in ethyl cation. This type of overlap stabilizes the carbocation because electron density from the adjacent sigma bond helps in dispersing the positive charge. Hyperconjugation is also possible in alkenes and alkylanes. Delocalization of electrons by hyperconjugation in the case of alkene can be depicted as in Fig. 12.4b. There are various ways of looking at the hyperconjugative effect. One of the way is to regard C, H bond as possessing partial ionic character due to resonance. 348 Chemistry. The hyperconjugation may also be regarded as no bond resonance. Problem 12.19 explain why CH3, 3C+, is more stable than CH and CH30 to 3 is the least stable cation. Solution hyperconjugation interaction in CH3, 3C+, is greater than in CH32 as the CH3, 3C+ has 9 CH bonds. In CH3, vacant p orbital is perpendicular to the plane in which CH bonds lie, hence cannot overlap with it. Thus, CH3 lacks hyperconjugative stability. 12th July 2010 Types of organic reactions and mechanisms. Organic reactions can be classified into the following categories: I. Substitution reactions, 2. Addition reactions, 3. Elimination reactions, 4. Rearrangement reactions. You will be studying these reactions in Unit 13 and later in Class 12. 12.8 Methods of purification of organic compounds. Once an organic compound is extracted from a natural source or synthesized in the laboratory, it is essential to purify it. Various methods used for the purification of organic compounds are based on the nature of the compound and the impurity present in it. The common techniques used for purification are as follows: I. Sublimation, 2. Crystallization, 3. Distillation, 4. Differential extraction, and V. Chromatography. Finally, the purity of a compound is ascertained by determining its melting or boiling point. Most of the pure compounds have sharp melting points and boiling points. New methods of checking the purity of an organic compound are based on different types of chromatographic and spectroscopic techniques. 12th August 2001 Sublimation. You have learnt earlier that on heating, some solid substances change from solid to vapor state without passing through liquid state. The purification technique based on the above principle is known as sublimation and is used to separate sublimable compounds from non-sublimable impurities. 12th August 2002 Crystallization. This is one of the most commonly used techniques for the purification of solid organic compounds. It is based on the difference in the solubilities of the compound and the impurities in a suitable solvent. The impure compound is dissolved in a solvent in which it is sparingly soluble at room temperature but appreciably soluble at higher temperature. The solution is concentrated to get a nearly saturated solution. On cooling the solution, pure compound crystallizes out and is removed by filtration. The filtrate, mother liquor, contains impurities and small quantity of the compound. If the compound is highly soluble in one solvent and very little soluble in another solvent, crystallization can be satisfactorily carried out in a mixture of these solvents. Impurities, which impart color to the solution, are removed by adsorbing over activated charcoal. Repeated crystallization becomes necessary for the purification of compounds containing impurities of comparable solubilities. 12th August 2003 Distillation. This important method is used to separate I. Volatile liquids from non-volatile impurities, and 2. The liquids having sufficient difference in their boiling points. Liquids having different boiling points vaporize at different temperatures. The vapors are cooled and the liquids so formed are collected separately. Chloroform, B.P 334K, and aniline, BP 457K, are easily separated by the technique of distillation, Fig 12.5. The liquid mixture is Organic Chemistry, Some Basic Principles and Techniques 349. Taken in a round bottom flask and heated carefully. On boiling, the vapors of lower boiling component are formed first. The vapors are condensed by using a condenser and the liquid is collected in a receiver. The vapors of higher boiling component form later and the liquid can be collected separately. Fractional distillation. If the difference in boiling points of two liquids is not much, simple distillation cannot be used to separate them. The vapors of such liquids are formed within the same temperature range and are condensed simultaneously. The technique of fractional distillation is used in such cases. In this technique, vapors of a liquid mixture are passed through a fractionating column before condensation. The fractionating column is fitted over the mouth of the round bottom flask, Fig. 12.6. Fig. 12.5 Simple Distillation. The vapors of a substance formed are condensed and the liquid is collected in conical flask. Fig. 12.6 Fractional Distillation. The vapors of lower boiling fraction reach the top of the column first, followed by vapors of higher boiling fractions. 350 Chemistry. Vapors of the liquid with higher boiling point condense before the vapors of the liquid with lower boiling point. The vapors rising up in the fractionating column become richer in more volatile component. By the time the vapors reach to the top of the fractionating column, these are rich in the more volatile component. Fractionating columns are available in various sizes and designs as shown in Fig. 12.7. A fractionating column provides many surfaces for heat exchange between the ascending vapors and the descending condensed liquid. Some of the condensing liquid in the fractionating column obtains heat from the ascending vapors and revaporizes. The vapors thus become richer in low boiling component. The vapors of low boiling component ascend to the top of the column. On reaching the top, the vapors become pure in low boiling component and pass through the condenser, and the pure liquid is collected in a receiver. After a series of successive distillations, the remaining liquid in the distillation flask gets enriched in high boiling component. Each successive condensation and vaporization unit in the fractionating column is called a Fig. 12.7. Different types of fractionating columns. Theoretical plate. Commercially, columns with hundreds of plates are available. One of the technological applications of fractional distillation is to separate different fractions of crude oil in petroleum industry. Distillation under reduced pressure. This method is used to purify liquids having very high boiling points and those which decompose at or below their boiling points. Such liquids are made to boil at a temperature lower than their normal boiling points by reducing the pressure on their surface. A liquid boils at a temperature at which its vapor pressure is equal to the external pressure. The pressure is reduced with the help of a water pump or vacuum pump. Fig. 12.8. Glycerol can be separated from spent lye in soap industry by using this technique. Steam distillation. This technique is applied to separate substances which are steam volatile and are immiscible with water. In steam distillation, steam from a steam generator is passed through a heated flask containing the liquid to be distilled. The mixture of steam and the volatile organic compound is condensed and collected. The compound is later separated from water using a separating funnel. In steam distillation, the liquid boils when the sum of vapor pressures due to the organic liquid, P1, and that due to water, P2, becomes equal to the atmospheric pressure, P. IP is equal to P1 plus P2. Since P1 is lower than P, the organic liquid vaporizes at lower temperature than its boiling point. Thus, if one of the substances in the mixture is water and the other, a water-insoluble substance, then the mixture will boil close to but below 373 K. A mixture of water and the substance is obtained, which can be separated by using a separating funnel. Aniline is separated by this technique from aniline water mixture. Fig. 12.9. 12th August 2004. Differential extraction. When an organic compound is present in an aqueous medium, it is separated by shaking. Organic chemistry, some basic principles and techniques. 351. Fig. 12.8. Distillation under reduced pressure. A liquid boils at a temperature below its vapor pressure by reducing the pressure. Fig. 12.9. Steam distillation. Steam volatile component volatilize, the vapors condense in the condenser and the liquid collects in conical flask. 352. Chemistry. Fig. 12.11. Column chromatography. Different stages of separation of components of a mixture. Fig. 12.10. Differential extraction. Extraction of compound takes place based on difference in solubility. It with an organic solvent in which it is more soluble than in water. The organic solvent and the aqueous solution should be immiscible with each other so that they form two distinct layers which can be separated by separatory funnel. The organic solvent is later removed by distillation or by evaporation to get back the compound. Differential extraction is carried out in a separatory funnel as shown in Fig. 12.10. If the organic compound is less, mixture get gradually separated from one another. The moving phase is called the mobile phase. Based on the principle involved, chromatography is classified into different categories. Two of these are A. Adsorption chromatography and B. Partition chromatography. A. Adsorption chromatography. Adsorption chromatography is based on the fact that different compounds are adsorbed on an adsorbent to different degrees. Commonly used adsorbents are silica gel and alumina. When a mobile phase is allowed to move over a stationary phase, adsorbent, the components of the mixture move by varying distances over the stationary phase. Following are two main types of chromatographic techniques based on the principle of differential adsorption. A. Column chromatography and B. Thin layer chromatography. Column chromatography. Column chromatography involves separation of a mixture over a column of adsorbent, stationary phase, packed in a glass tube. The column is fitted with a stopcock at its lower soluble in the organic solvent, a very large end, Fig. 12.11. The mixture adsorbed on quantity of solvent would be required to extract even a very small quantity of the compound. The technique of continuous extraction is employed in such cases. In this technique, same solvent is repeatedly used for extraction of the compound. 12th August 2005 Chromatography. Chromatography is an important technique extensively used to separate mixtures into their components, purify compounds, and also to test the purity of compounds. The name chromatography is based on the Greek word chroma, for colors, since the method was first used for the separation of colored substances found in plants. In this technique, the mixture of substances is applied onto a stationary phase, which may be a solid or a liquid. A pure solvent, a mixture of solvents, or a gas is allowed to move slowly over the stationary phase. The components of the organic chemistry, some basic principles and techniques. 353. Adsorbent is placed on the top of the adsorbent column packed in a glass tube. An appropriate eluent, which is a liquid or a mixture of liquids, is allowed to flow down the column slowly. Depending upon the degree to which the compounds are adsorbed, complete separation takes place. The most readily adsorbed substances are retained near the top, and others come down to various distances in the column. Fig. 12.11. Thin layer chromatography. Thin layer chromatography, TLC, is another type of adsorption chromatography, which involves separation of substances of a mixture over a thin layer of an adsorbent coated on glass plate. A thin layer, about 0.2 mm thick, of an adsorbent, silica gel or alumina, is spread over a glass plate of suitable size. The plate is known as thin layer chromatography plate or chromoplate. The solution of the mixture to be separated is applied as a small spot about 2 cm above one end of the TLC plate. The glass plate is then placed in a closed jar containing the eluent, Fig. 12.12a. As the eluent rises up the plate, the components of the mixture move up along with the eluent to different distances depending on their degree of adsorption, and separation takes place. The relative adsorption of each component of the mixture is expressed in terms of its retardation factor, i.e. RF value. Fig. 12.12b. RF is equal to distance moved by the substance from baseline Kiss smiley distance moved by the solvent from baseline, y. The spots of colored compounds are visible on TLC plate due to their original color. The spots of colorless compounds, which are invisible to the eye but fluoresce in ultraviolet light, can be detected by putting the plate under ultraviolet light. Another detection technique is to place the plate in a covered jar containing a few crystals of iodine. Spots of compounds, which absorb iodine, will show up as brown spots. Sometimes an appropriate reagent may also be sprayed on the plate. For example, amino acids may be detected by spraying the plate with ninhydrin solution, Fig.12.12b. Partition chromatography. Partition chromatography is based on continuous differential partitioning of components of a mixture between stationary and mobile phases. Paper chromatography is a type of partition chromatography. In paper chromatography, a special quality paper known as chromatography paper is used. Chromatography paper contains water trapped in it, which acts as the stationary phase. A strip of chromatography paper spotted at the base with the solution of the mixture is suspended in a suitable solvent or a mixture of solvents, Fig. 12.13. This solvent acts as the mobile phase. The solvent rises up the paper by capillary action and flows over the spot. The paper selectively retains different components according to their differing partition in the two phases. The paper strip so developed is known as a chromatogram. The spots of the separated colored compounds are visible at different heights from the position of initial spot on the chromatogram. The spots of the separated Fig.12.12b developed chromatogram. Colorless compounds may be observed either. Fig.12.12a thin layer chromatography. Chromatogram being developed. 354 chemistry. 5H2O plus CuSO4 CuSO4.5 H2O white blue. 12th September 2002 detection of other elements. Nitrogen, sulfur, halogens and phosphorus present in an organic compound are detected by Lassen's test. The elements present in the compound are converted from covalent form into the ionic form by fusing the compound with sodium metal. Following reactions take place: Na plus C plus N Na CN. To Na plus S Na to S. Na plus X Na X. X is equal to Cl, Br or I, C, N. S and X come from organic compound. Cyanide, sulfide and halide of sodium so formed on sodium fusion are extracted from the fused mass by boiling it with distilled water. This extract is known as sodium fusion extract. A. Test for nitrogen. The sodium fusion extract is boiled with iron, 2, sulfate, and then acidified with concentrated sulfuric acid. The formation of Prussian blue color confirms the presence of nitrogen. Sodium cyanide first reacts with iron, 2, sulfate and forms sodium hexacyanoferrate, 2. On heating with concentrated sulfuric acid some iron, 2, ions are oxidized to iron, 3, ions which react with sodium hexacyanoferrate, 2, to produce iron, 3, hexacyanoferrate, 2, ferriferocyanide, which is Prussian blue in color. 6 Cn plus Fe2 plus Fe, Cn, 6, 4. 3, Fe, Cn, 6, 4, plus 4 Fe3 plus Fe4, Fe, Cn, 6, 3. XH2O Prussian blue, B. Test for sulfur. A. The sodium fusion extract is acidified with acetic acid and lead acetate is added to it. A black precipitate of lead sulfide indicates the presence of sulfur. S2 plus Pb2 plus Pbs black, B. On treating sodium fusion extract with sodium nitroprusside, appearance of A. Fig.12.13 Paper Chromatography. Chromatography paper into different shapes. Under ultraviolet light or by the use of an appropriate spray reagent as discussed under thin layer chromatography. 12.9 Qualitative Analysis of Organic Compounds. The elements present in organic compounds are carbon and hydrogen. In addition to these, they may also contain oxygen, nitrogen, sulfur, halogens, and phosphorus. 12th September 2001 Detection of carbon and hydrogen. Carbon and hydrogen are detected by heating the compound with copper 2 oxide. Carbon present in the compound is oxidized to carbon dioxide, tested with lime water, which develops turbidity, and hydrogen to water, tested with anhydrous copper sulfate, which turns blue. C plus to CuO to Cu plus CO2. 2H plus CuO Cu plus H2O. CO2 plus CaO to CaCO3 plus H2O. Organic Chemistry, Some Basic Principles and Techniques 355. Violet color further indicates the presence of sulfur. S2 plus Fe, Cn, 5 No, 2 Fe, Cn, 5 numbers, 4 violet in case nitrogen and sulfur both are present in an organic compound, sodium thiocyanate is formed. It gives blood red color and no Prussian blue since there are no free cyanide ions. Na plus C plus N plus S NiCN Fe 3 plus SCN, Fe, SCN 2 plus. Blood red if sodium fusion is carried out with excess of sodium, the thiocyanate decomposes to yield cyanide and sulfide. These ions give their usual tests. NiCN plus to NaCN plus Na to S, C, test for halogens. The sodium fusion extract is acidified with nitric acid and then treated with silver nitrate. A white precipitate, soluble in ammonium hydroxide shows the presence of chlorine. A yellowish precipitate, sparingly soluble in ammonium hydroxide shows the presence of bromine, and a yellow precipitate, insoluble in ammonium hydroxide shows the presence of iodine. X plus Ag plus AgX, X represents a halogen, Cl, Br or I. If nitrogen or sulfur is also present in the compound, the sodium fusion extract is first boiled with concentrated nitric acid to decompose cyanide or sulfide of sodium formed during Lassen's test. These ions would otherwise interfere with silver nitrate test for halogens. D. Test for phosphorus. The compound is heated with an oxidizing agent, sodium peroxide. The phosphorus present in the compound is oxidized to phosphate. The solution is boiled with nitric acid and then treated with ammonium molybdate. A yellow coloration or precipitate indicates the presence of phosphorus. Na3PO4 plus 3HNO3H3PO4 plus 3 nano 3H3PO4 plus 12 NH4 2Mu4 plus 21 HNO3 ammonium molybdate NH4 3PO4.12 Mu3 plus 21 NH4 No3 plus 12 H2O ammonium phosphomolybdate. 12.10 Quantitative Analysis. The percentage composition of elements present in an organic compound is determined by the methods based on the following principles. 12th October 2001 Carbon and hydrogen. Both carbon and hydrogen are estimated in one experiment. A known mass of an organic compound is burnt in the presence of excess of oxygen and copper 2 oxide. Carbon and hydrogen in the compound are oxidized to carbon dioxide and water respectively. CXHY plus X plus Y slash 4 O2X CO2 plus Y slash 2 H2O. The mass of water produced is determined by passing the mixture through a weighed U-tube containing anhydrous calcium chloride. Carbon dioxide is absorbed in another U-tube containing concentrated solution of potassium hydroxide. These tubes are connected in series, Fig. 12.14. The Fig. 12.14 estimation of carbon and hydrogen. Water and carbon dioxide formed on oxidation of substance are absorbed in anhydrous calcium chloride and potassium hydroxide solutions respectively contained in U-tubes. 356 Chemistry. Increase in masses of calcium chloride and potassium hydroxide gives the amounts of water and carbon dioxide from which the percentages of carbon and hydrogen are calculated. Let the mass of organic compound be mg, mass of water and carbon dioxide produced be m1 and m2g respectively. Percentage of carbon is equal to 12/100 to 44. Percentage of hydrogen is equal to 101/18. Problem solution 12 is equal to Fig. 12.15 Damas method. The organic compound yields nitrogen gas on heating it with copper 2 oxide in the presence of CO2 gas. The mixture of gases is collected over potassium hydroxide solution in which CO2 is absorbed and volume of nitrogen gas is determined. Percentage of hydrogen is equal to 0.1014 0.246 is equal to 4.58%. 12th October 2002 Nitrogen. There are two methods for estimation of nitrogen, I. Damas method and 2. Kaldahal's method. I. Damas method. The nitrogen-containing organic compound, when heated with copper oxide in an atmosphere of carbon dioxide, yields free nitrogen in addition to carbon dioxide and water. CXH winds it plus 2x plus y slash 2 CO. X CO2 plus y slash 2 H2O plus Z slash 2 N2 plus 2x plus y slash 2 Cu. Traces of nitrogen oxides formed, if any, are reduced to nitrogen by passing the gaseous mixture over a heated copper gauze. The mixture of gases so produced is collected over an aqueous solution of potassium hydroxide which absorbs carbon dioxide. Nitrogen is collected in the upper part of the graduated tube, Fig. 12.15. Organic chemistry, some basic principles and techniques 357. Let the mass of organic compound is equal to mg volume of nitrogen collected is equal to V1 ml room temperature is equal to T1 K. 111. 273 volume of nitrogen at STP is equal to 760 PVT. Let it be VML, where P1 is equal to atmospheric pressure, aqueous tension. 22400 ml N2 at STP weighs 28 g. To 28 ml N at STP weighs is equal to G 22,400 VV. Percentage of nitrogen is equal to 28,100. 22,400. V. Calculate the percentage composition of nitrogen in the compound. Aqueous tension at 300 K is equal to 15 mm. Solution. Volume to 737 is equal to 40. 22,400 ml of N2 at STP weighs is equal to 28 g. 2841.91 is equal to 17.46%. Two. Kaldahal's method. The compound containing nitrogen is heated with concentrated sulfuric acid. Nitrogen in the compound gets converted to ammonium sulfate, Fig. 12.16. The resulting acid mixture is then heated with excess of sodium. Fig. 12.16 Kaldahal Method. Nitrogen-containing compound is treated with concentrated H2SO4 to get ammonium sulfate, which liberates ammonia on treating with NaOH. Ammonia is absorbed in known volume of standard acid. 358 Chemistry. Fig. 12.17 Carius Method. Halogen-containing organic compound is heated with fuming nitric acid in the presence of silver nitrate hydroxide. The liberated ammonia gas is absorbed in an excess of standard solution of sulfuric acid. The amount of ammonia produced is determined by estimating the amount of sulfuric acid consumed in the reaction. It is done by estimating unreacted sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of acid taken and that left after the reaction gives the amount of acid reacted with ammonia. Organic compound plus H2SO4, NH4, to SO4. 224 3 to NaOH Na so NHHO. To NH3 plus H2SO4, NH4, to SO4. Let the mass of organic compound taken is equal to mg volume of H2SO4 of molarity, M, taken is equal to V ml volume of NaOH of molarity, M, used for titration of excess of H2SO4 is equal to V1 ml of NaOH of molarity, M, is equal to V1 to ml of H2SO4 of molarity, M volume of H2SO4 of molarity, M unused is equal to VV12 ml. VV12 ml of H2SO4 of molarity, M, is equal to 2 VV12 ml of NH3 solution of molarity, M. 14 m to VV to 1 G N 1000. 14 m to VV to 100% of N is equal to 1000 m. 1.4 m to 1 is equal to VV. M. Kaldahal method is not applicable to compounds containing nitrogen in nitro and azo groups and nitrogen present in the ring, e.g. pyridine, as nitrogen of these compounds does not change to ammonium sulfate under these conditions. Problem 12.22. During estimation solution 1 m of 10 ml 14 to 1000 g percentage of nitrogen is equal to 560%. 12th October 2003 Halogens Carriers method. A known mass of an organic compound is heated with fuming nitric acid in the presence of silver nitrate contained in a hard glass tube known as Carrier's tube, Fig. 12.17, in a furnace. Carbon and hydrogen. Organic chemistry, some basic principles and techniques 359. Present in the compound are oxidized to carbon dioxide and water. The halogen present forms the corresponding silver halide, AgX. It is filtered, washed, dried and weighed. Let the mass of organic compound taken is equal to mg mass of AgX formed is equal to m1g. 1 mole of AgX contains 1 mole of X. Mass of halogen in m1g of AgX. Atomic mass of Xg1 molecular mass of AgX m. Percentage of halogen. Atomic mass molecular S of M1. M. 1. Problem 12.23. In Carrier's method of estimation of halogen, 0.15 g of an organic compound gave 0.12 g of AgBr. Find out the percentage of bromine in the compound. Solution. Molar mass of AgBr is equal to 100 and 8 plus 80 is equal to 188 g mol 1. 188 g AgBr contains 80 g bromine. 0.12 g AgBr contains 80.012. 188 g bromine. 80.1 to 100% of is equal to 34.04%. October 2004 Sulfur, a known mass of an organic compound, is heated in a Carrier's tube with sodium peroxide or fuming nitric acid. Sulfur present in the compound is oxidized to sulfuric acid. It is precipitated as barium sulfate by adding excess of barium chloride solution in water. The precipitate is filtered, washed, dried and weighed. The percentage of sulfur can be calculated from the mass of barium sulfate. Let the mass of organic compound taken is equal to mg and the mass of barium sulfate formed is equal to m1g. 1 mole of BaSO4 is equal to 233 g BaSO4 is equal to 32 g sulfur. M1g BaSO4 contains 30 to 233 mg sulfur. 30 to 101% of sulfur is equal to 233. Problem 12.24. In sulfur estimation, 0.157 g of an organic compound gave 0.4813 g of barium sulfate. What is the percentage of sulfur in the compound? Solution. Molecular mass of BaSO4 is equal to 137 plus 32 plus 64 is equal to 233 g. 233 g BaSO4 contains 32 g sulfur. 0.4813 g BaSO4 contains 30 to 0.4813 233 g sulfur. 30 to 0.4813 100% of sulfur is equal to 233 0.157 is equal to 42.10%. 12th October 2005 Phosphorus. A known mass of an organic compound is heated with fuming nitric acid whereupon phosphorus present in the compound is oxidized to phosphoric acid. It is precipitated as ammonium phosphomolybdate, NH4, 3PO4.12 Mu3, by adding ammonia and ammonium molybdate. Alternatively, phosphoric acid may be precipitated as MgNH4PO4 by adding magnesia mixture, which on ignition yields Mg2P2O7. Let the mass of organic compound taken is equal to mg, and mass of ammonium phosphomolybdate is equal to m1g. Molar mass of NH4, 3PO4.12 Mu3 is equal to 1877 g. Percentage of phosphorus is equal to 31 101 1877. M %. If phosphorus is estimated as Mg2P2O7, percentage of phosphorus is equal to 60 to 101%, 222. mm 360 Chemistry. Summary. In this unit, we have where 222U is the molar mass of Mg2P2O7. M, the mass of organic compound taken, M1 the mass of Mg2P2O7 formed, and 62, the mass of two phosphorus atoms present in the compound Mg2P2O7. 12th October 2006 Oxygen. The percentage of oxygen in an organic compound is usually found by difference between the total percentage composition, 100, and the sum of the percentages of all other elements. However, oxygen can also be estimated directly as follows. A definite mass of an organic compound is decomposed by heating in a stream of nitrogen gas. The mixture of gaseous products containing oxygen is passed over red-hot coke when all the oxygen is converted to carbon monoxide. This mixture is passed through warm iodine pentoxide, I2O5, when carbon monoxide is oxidized to carbon dioxide producing iodine. Compound heat O2 plus other gaseous products. To C plus O2 1373 K2 Co times 5 A. I2O5 plus 5 Co I2 plus 5 Co2 times 2 B. On making the amount of Co produced in equation A equal to the amount of Co used in equation B, by multiplying the equations A and B by 5 and 2 respectively, we find that each mole of oxygen liberated from the compound will produce 2 moles of carbon dioxide. Thus 88 G carbon dioxide is obtained if 32 G oxygen is liberated. Let the mass of organic compound taken be mg, mass of carbon dioxide produced be m1g. m1g carbon dioxide is obtained from 30 to 188 mgO2. Percentage of oxygen is equal to 30 to 101 88 mm%. The percentage of oxygen can be derived from the amount of iodine produced also. Presently, the estimation of elements in an organic compound is carried out by using microquantities of substances and automatic experimental techniques. The elements, carbon, hydrogen and nitrogen present in a compound are determined by an apparatus known as CHN elemental analyzer. The analyzer requires only a very small amount of the substance, 1 to 3 milligrams, and displays the values on a screen within a short time. A detailed discussion of such methods is beyond the scope of this book.